The theme of my talk is multi-wavelength dataset of aerosol extinction profiles retrieved from GOMOS stellar occultation measurements. GOMOS was operating on board ENVISAT in years 2002-2012. And its name, its full name, Global Ozone Monitoring by Occultation of Stars. And the main advantage of occultation principle, it is self-calibration. When stellar light observed through atmosphere divided by stellar light, stellar spectra observed above the atmosphere, we will get transmittance or transmittance spectra, which are the basis for retrievals of trace gases from occultation instruments. GOMOS is equipped with UV and visible photometers, and also with two near-infrared photometers, or with UV visible spectrometers and near-infrared spectrometers, and with two fast photometers operating in blue and red wavelength ranges. The main principle of GOMOS retrievals, it is usually the information profiles of ozone and other trace gases. They are retrieved for each occultation. And first, the data processing starts with correction of refractive effects, refractive attenuation and scintillations. This doesn't work. And then we go to inversion, which is split into two steps. First, it is spectral inversion, or it is using absorption and scattering cross-section. We retrieve the information about slant column densities, and then vertical inversion, and for which is performed for each gases separately. And from collection of horizontally integrated column density, we retrieve vertical profiles of different species. So this is a standard two-step inversion of GOMOS data. And the GOMOS aerosol profiles, they were one of the, together with ozone, one of the main data products. And it contains important information about aerosols in the stratosphere, and even it was used in climate-related studies already a long time ago. That is a picture from IPCC report. Laser pointer, okay. Here, and the main problems, main challenges for GOMOS aerosol retrievals, it is that spectral dependence of aerosol cross-section is not known. It depends on particle size distribution in the atmosphere. For GOMOS, we have a rather short wavelength range. We don't have measurements close to 1 micron. And the third, also natural phenomenon, it is modulation of GOMOS transmittance spectra by not fully corrected scintillations, which are seen in the case of oblique occultations. And this is also influence retrievals and make retrievals of aerosols challenging. And for basic retrievals, we need to assume something related about aerosol spectral dependence. There are two main previous retrievals. One is official, IPF version 6, and second, it is advanced aerosol focused retrievals AirGOM. They also, both these retrievals, they are in two steps retrievals, and they are for each occultation separately. In AirGOM, it is also used data from a near-infrared spectrometer. Slightly different fit, but basically simultaneous fit. They use slightly different law for aerosol spectra. They modeled by a second-order polynomial in direct wavelengths in IPF version 6, and in inverse wavelengths for AirGOM. Also slightly different vertical inversion. using for each species separately in version 6, or retrieving all species together in ARGOM. And the known problems that it is spectral dependence of aerosol extinction is not always realistic. So this is typical pictures for collection in IPF version 6. So this shape of aerosol extinction spectra. They are better in ARGOM, but still sometimes this dependence is not realistic. And it is also known because of its interference between ozone and aerosol retrievals. Version 6 has strong ozone bias and also aerosol bias in the UTLS. And also known problem with ARGOM, it is sometimes we observe negative values at shorter or at longer wavelengths. But more details on ARGOM retrievals, please visit poster by Christine Bingen on Thursday. In our retrievals, we used slightly different approach. We use monthly and zonally average transmittance spectra as starting point for our retrievals. The advantage is that it is significantly better signal-to-noise ratio. So this is examples of the average transmittances. And second, that it is residual scintillations which are random effect. They are simply removed. This illustration, it is typical transmittance spectra in usual conditions, and in red it is transmittances at 20 kilometers. And we see that in normal conditions it is larger than in volcanic conditions. So the transmittance are lower, aerosol optical depth is larger. Our idea for retrievals is very simple. From transmittance spectra, from which already removed refractive effects, we remove contributions by ozone, by relay scattering, by NO2 and NO3. And the remaining part, it is due to aerosols. For NO2 and NO3, we use data retrieved in GOMOS version 6 data. They are from DOAS retrievals. For ozone, we also use DOAS type retrieval in SHPE channel, in SHPE band. And the remaining residuals is smoothed and taken at 9 wavelengths. And this collection of wavelengths is selected in such a way that have the same wavelengths as also other instrument measures. And so this is the result of our spectral inversion. And the vertical inversion is performed in the same way as in GOMOS version 6. Vertical inversion is linear, very simple, and it is regularized by Tikhonov type regularization. And the actual resulting resolution of retrieved aerosol profiles is around 3 kilometers. When we compare our results with SAGE-2, these are our data for September 2002, and we see similar spectral dependence, larger at shorter wavelengths. Above 20 kilometers it is similar, but below 20 kilometers it is different. And when compare profiles from SAGE-2 and GOMOS, we see that very good agreement above 20 kilometers, and below 20 kilometers GOMOS extinction is larger. And we think that it is influence of very thin cirrus clouds, because of when we compared with original SAGE data without additional cloud filtering, then we will get very similar results. Comparing to ARGOM, the same case for the same months, the same latitude range. We also observe rather similar results above 20 kilometers and different results below 20 kilometers. And in our retrievals, results larger at shorter wavelengths, while opposite behavior is observed in ARGOM data. And also this is the profiles of angstrom exponent for our retrievals using different combination. It is slightly increasing with wavelengths in range from 1 to 3, while for ARGOM it can be below 1 and closer to 4. At 525 and 750 nanometers, we compared with data from different instruments with SAGE-2, so this panel on 225 nanometers. Also with ARGOM and also with Skiamaki retrievals, with which allows information also at nearly all wavelengths. This retrievals based on retrieval of particle size distribution. And in 750 nanometers, we have compared our data with the ARGOM Skiamaki and also with Azaris data. And as general, above 20 kilometers, ARGOM's aerosol extinction profile in very close to data from other instruments. But below, close to in the vicinity of tropical tropopause, GOMOS reports larger aerosol extinction. And this feature is present also in ARGOM dataset. From the point of long-term time series of aerosol extinction coefficient, here it is time series at 20 kilometers for different wavelengths, 525, 772, and 750 nanometers. And we see clearly enhancement associated with volcanic activity. So we provide the data with 9 wavelengths, and we see typical behavior of typical spectral dependence of aerosol extinction coefficient, larger at shorter wavelengths. We see also clear enhancement related to volcanic periods. If we compare with similar figure based on ARGOM, ARGOM shows similar behavior in the beginning of GOMOS mission, but after 2009, the spectral dependence not actually it is can be not realistic, and also we even here we observe presence of negative values at 750 nanometers or at shorter wavelengths. We also would like to demonstrate that GOMOS new retrievals is in very good agreement with other data from other instruments in terms of long-term variations and long-term variability of stratospheric aerosols. So these are time series and different line indicate data from Azaris, Skiamaki, OMS, GOMOS with black, SAGE-2, SAGE-3 on International Space Station. And also here it is a merged line which corresponds to climate data record of stratospheric aerosols, but more details on creation of this long-term climate data of stratospheric aerosol will be in my presentation on Friday. And new GOMOS data participated in this data set. So, coming to summary, the GOMOS aerosol retrieval algorithm from average transmittance spectra has been developed and applied to the whole GOMOS dataset from 2002 to 2012. We provide extinction profiles in the altitude range from 10 to 40 kilometers at 9 different wavelengths from 400 to 750 nanometers. The data are monthly average in 10 degrees from 90 south to 90 north. We think that our resolve extinction profile show realistic wavelength dependence, and they are in good agreement with other data sets. And this experience with aerosol retrievals is also useful for forthcoming ALTIUS mission. Thank you.